the one thing that people ask me the most about, and I can see why when I looked at what I wrote, was this particular problem from last spring. So find the integral from 0 to 1, the integral from x to the cubed root of x of 24 square root of 1 minus y to the 4th dy dx. I like this problem. And I'm going to tell you right now, I'm the one who wrote this problem. And probably by then you won't be surprised when you see what happens. So this is a problem where you have integration. It's a two-dimensional integration. And one of the things, if you just see a two-dimensional integration problem and you say, fine, you should be highly suspicious about what you need to do. Because it seems like that's almost too straightforward. And now that you stare at it, you're like, oh, I see what's the problem. See, if I integrate this with respect to y, I'm going to have a bad day. Because that's hard to integrate with respect to y. So what's embedded in this problem is we need to change the order of integration. So this is a change the order of integration problem. So why do we change the order? Well, if we can't integrate with respect to y, maybe we can integrate with respect to x. So here we go. So we have the, well, if we're going to change the order, we have to do a quick sketch. So what do we have? Well, our bounding curves, y equals x, looks like that. It's a pretty easy bounding curve. Then here we have y equals the cubed root of x, x to the 1/3. Now the cubed root of x looks like x cubed, except you turn it on its side. And so what happens is it comes through and then goes something like that. So here we have y equals x. Here we have y equals x to the 1/3. And then we're looking for this part in between, because if you check, they both pass through the same point at 1. In particular, when you plug in x equals 1, you're going to get out that y equals 1. All right, so there's our region. So we need to change our order. So we say, all right, if we're changing our order, our function doesn't change. That doesn't depend on order. So we go dx dy. I like to work from the outside in. I say, well, where does y go from? Well, it goes from 0 to 1. Now, where does x go from? So I need to rewrite these curves. So y equals x becomes x equals y. Y equals x to the 1/3. Well, let's cube both sides. That would become y cubed equals x. And now I want to go from left to right. So when I'm slicing up in a horizontal fashion, which is what I'm switching to, it's low value on the left, high value on the right. So we're going to go y cubed to y. So the nice thing is that this integral, at least the first stage, is fairly straightforward. 24 square root 1 minus y to the 4th. And then we have x, evaluated from x equals y cubed to x equals y, which is 24 square root of 1 minus y to the 4th. And then we have y minus y cubed. Now at this stage, here's where the problem gets interesting. It's like, all right, how do you actually integrate this? Now oftentimes you say, oh, I know, I just make an easy substitution and life is good. And you say, well, okay, like 1 minus y to the 4th, that's the function on the inside. Take the derivative of that, you'd get a y cubed, which I have, but I don't have a y minus. So here is when we start saying, all right, what can you do? What can you do? Now, one of the things about integration is it's this really cool thing is you can pull things apart. So we'll pull them apart. So what do I mean? Well, I can distribute this 24 square root of 1 minus y to the 4th to the inside. So you get 24 square root of 1 minus y to the 4th times y minus 24 square root of 1 minus y to the 4th times y cubed. And then I'll treat these as two separate integrals. So I have 0 to 1, 24 square root of 1 minus y to the 4th times y dy minus 0 to 1, 24 square root of 1 minus y to the 4th times y cubed dy. Now comes the fun part. We say, hey, you know, we had that idea before, which is if you let u be the inside, namely 1 minus y to the 4th, then what happens is that du would be negative 4y cubed. Now, in the write-up I said u equals y to the fourth, and then I skipped an intermediate step where there's a second round of substitution, but I'll go ahead and do that here this time. So what happens to this integral? Well, I can pull the 24 apart and write it as 6 times 4, because I need a 4y cubed. So what ends up happening for just this piece is we get the following. We have a minus integral. Now we got to do the bounds. So they were from 0 to 1. So we plug in 0, we get 1. Plug in 1, we get 0. And then we have the 6, because nothing happens to that. But then a 4y cubed dy, that's going to give us a minus du. And then the square root of 1 minus y to the fourth becomes a u to the 1/2. Well, I can take that minus and flip the bounds. So I get minus, I'll go ahead and pull out the 6 too, 0 to 1 of u to the 1/2 du. So that's minus 6. And then here, it's u to the 3/2 times 2/3. And evaluate from 0 to 1. If you plug in 0, you get 0. If you plug in 1, well, 1 to the 3/2 is 1. So you get minus 6 times 2/3, which is negative 4. Okay, so that's the first, or rather I should say the second integral. What about the other one? Well, here's the thing. You don't have to do the same technique on each integral. You're allowed to mix and match. You might say, well, on this one, I'll use this idea. On this other one, I'll use a different idea. So what do we mean by a different idea? So let's look at this integral. Say, okay, the problem here is we can't do that y to the fourth substitution. We don't have a y cubed there. But we do have a y. And if we have a y, well, that means we really have like a 2y. And the reason I say that is when you're looking for substitutions, you oftentimes say, if I can't see what's clearly the function on the inside, look for something that's an easy derivative. And like, oh, 2y I recognize as the derivative of y squared. So this one, we can make a different substitution. U equals y squared. And then du would be 2y dy. So I'm going to take the 24. Again, I'm going to pull it apart. 2 times 12. And so what do we get? Well, we get that this will become the integral. Now the bounds, you plug in 0 and 1, and it turns out that 0 and 1 happen to satisfy that 0 squared equals 0 and 1 squared equals 1. So we're still going 0 to 1. We have that 12. And then we have the square root of 1 minus u squared du. Because the 2y dy becomes the du. And y to the fourth is y squared squared. So it becomes u squared. And here we say, all right, pull out the 12. And what do we see? Well, we see an integral that looks like a Calc 2 integral, unless we remember our Calc 1 ideas. That's a circle. In particular, we can say that this integral, I can think of it as asking for the area of that part of the circle, 1/4 of the unit circle. So we can interpret and say, okay, this is the area, which is 1/4 of pi r squared, but radius is 1, so it's 1/4 pi. So we get 12 times 1/4 pi, or 3 pi. And now we put these two together, and so our final answer is 3 times pi minus 4. And that's the answer. All right. So that was one problem. Another problem that people wanted to look at, well, not necessarily this particular problem, but a problem like this. So let's talk about this one. This was from the exam from last spring. Now, this is a problem that you might call a WTF problem. By WTF standing for, what's the flux? Right? So when you see a problem that's talking about flux, and there's a really key word that you're looking for. The key word you're looking for is the word flux. So that's how you'll know if it's a flux problem. Flux is, again, a fancy way of saying flow. So when you see that word, you're like, okay, we're talking about flow. Now, flow can happen in many different contexts. So when I talk about flow, you have to understand the context. So what do I mean by it can happen in different contexts? It can happen for a curve. It can happen for a closed curve. It can happen for a three-dimensional surface. Now, generally speaking, we're not going to test you on the curve. For a closed curve, the way it will turn out to be is it's the integral of your region over your divergence. But that is a story that we're really going to save for after the exam. So almost surely, when we talk about flux, it's in this setting, namely a surface. So let's talk about what the flux becomes. Now, I don't want to rederive the formula because I want to say, look, we need to know how do we do it. So let's talk about what you're looking for. You want a surface which has the form z equals f of xy. So you need a surface. You need an orientation. And normally what you're looking for is you're looking for the following key phrase, upward. And they'll always tell you an orientation, either up or down. And 95% of the time, it's up. Okay, so we have an orientation. If, by the way, they change it to down, just throw a minus. Okay, so you have a surface, you have an orientation, and the other thing you have is you have a vector field. So the vector field is modeling how things are moving, how things are going through your space. So it's a vector field of f of m and p. And I should add that your surface is over a particular region R. So these are your pieces. You have a surface which is a function over region R. You have an orientation given to you, and you have a vector field. Now, once you have all these pieces, then what happens is that you get a nice formula. And so if you remember the formula, it's actually not a hard problem. And if you don't remember the formula, you can just rederive it. It only takes about 15 minutes to do that. So here's how it works. You integrate over your region minus m fx minus n fy plus p dA. That's the formula. So if you remember this, you're probably halfway there. Because usually this is the hard part. All right. So we have our nice region set up. What comes next? Well, okay, so here, next thing to think about. Do you want me to talk to you about the derivation of this, or are you okay with believing that this is just what it is? Okay, you sound like you're okay. If it helps you remember, just think of it as the dot product of your f with what your gradient would be if you took z minus f, minus fx, minus fy, and 1. So that can be a way to remember it if you're trying to remember exactly what it looks like. So from here, it's going to be basically just do the work. So we do the work. All right. So we have our function. There's our function. We have our f, our vector field. And we have our region. And it's described to us as sort of x squared plus y squared is between 1 and between 4. Okay, so right away we notice, like, hey, this region, it's a circle inside another circle. So here's our region R. Now when you see a circle inside of a circle, what does that suggest? Polar. Yeah. So if you start seeing circles showing up in your regions, like, I should try doing polar with this problem. Now, do we have to? Well, it depends. We might get lucky, and it might be the case that what we end up integrating is so simple, we don't have to do anything. We just have to find area. That often happens in certain problems. For example, Green's theorem, that happens frequently, where it's like, oh, here's this complicated integral. Ha, ha, ha. It's just the area. So you might get lucky. So first, find out what you're integrating before you start panicking and trying to set everything up in polar. So we'll come back to that in a second. All right. So our flux, following the formula, is the integral over our region of, and okay, so here's our m and p. So minus m, that's x, times f sub x. Well, this is 3x squared plus 3y squared to the 1/2. So if I take derivative with respect to x, f sub x, the 1/2 comes down, 3x squared plus 3y squared to the minus a half, and then times that by 6x. The half goes into 6, which leaves us with 3x over the square root of 3x squared plus 3y squared. Okay, so there's our f sub x. Okay, so there minus m fx. Then the next term, minus n fy. So minus y. And fy is going to be essentially the same. The only thing that's different is the 6x becomes a 6y. So it would be 3y over the square root of 3x squared plus 3y squared. And then plus p plus xy squared. And dA. All right, so now we've got this part set up. Well, we should probably clean it up. Now, there's a couple things we can do. By the way, one of the things we could have done is we could have factored out a 3 out of that square root. So I could write this as the square root of 3 times the square root of x squared plus y squared. And if I have 3 over square root of 3, that's the square root of 3 times x over the square root of x squared plus y squared. So let's put this together. Let's clean up a little bit. Integral over our region. And the first term, well, again, thinking about pulling out the square root of 3's and simplifying, I'll have minus square root of 3 times x squared over square root of x squared plus y squared. And then here, it's also the same thing, so I can just sort of pull this out. Y squared. So x squared plus y squared over square root of x squared plus y squared plus xy squared. So this becomes the integral over our region of minus square root of 3 times the square root of x squared plus y squared plus xy squared. Now, one of these integrals is really easy, and the other one is not so bad. Which one do you want to do first? I'll go ahead and give you a hint. What's that integral going to be? And how do we know? That integral will be 0, right? Because if you're going to get an answer, it's going to be 0. Otherwise, you have to work. Now you're probably like, what? How is that 0? Look at the shape of your region. It's symmetrical. It's highly symmetrical. Look at this function, xy squared. What happens is if I take a piece and I flip it across and compare it to a piece over there, the pieces match up. In other words, it's the same little part. What happens to the value of this expression? It will. One's negative, one's positive. So what will happen is that you'll get cancellation. So this cancels out by symmetry. Essentially, this is an odd function with respect to the y-axis. So this equals 0. Now, if you didn't see that and you did the integral, it would still come out to be 0. In the interest of time, I just want to speed that up and save myself a step. I'm not saying that this is going to happen on the exam. I'm just saying these are like the fun tools that you want to have in your belt as you leave calc. Be like, look at me. I know symmetry. And then we're like, ooh, wow, that person knows symmetry. Don't mess with them. Okay. All right. So let's actually do the integral. See, this integral, we actually have to do something because it's not so clear what it is. So this will be an integral. And we already said we're switching to polar. What happens to square root of x squared plus y squared? Becomes r. Because they create the square root. dA, r dr d theta. So there's a second r. So I'll write that as r squared. Theta, well, we go all the way around. 0 to 2 pi. dr, well, we go from the inner circle to the outer circle. So that is 1 to 2. Well, this is an integral where you can break it into two parts. 0 to 2 pi d theta, 1 to 2 minus root 3 r squared dr. So The first integral, 2 pi, because it's just 0 to 2 pi d theta. The second integral, well, there's the minus root 3. Then it's r cubed over 3, evaluated from r equals 1 to r equals 2. And if you plug that in, well, you'll get 8, because that's 2 cubed, minus 1, which is 1 cubed, so that will become a 7. So that r cubed, once you evaluate, becomes 7. So we end up with 7 times 2, that's 14. There's a pi, there's a square root of 3, there's a 3, and of course, don't forget that minus, because apparently I forget minuses a lot. And there's the answer. Did I forget a minus?
No, I got a question.
Sure.
Do you know when you can break apart the integral, when you broke it apart with the d theta and the dr?
So how do I know when I can break apart the integral? So in other words, I have this double iterated integral, and I want to separate it into 2. The answer is, first off, you do not have to do that. If you're not comfortable doing that, don't do it, because you should do what you are comfortable with. The exam is not a time to be uncomfortable. You should imagine yourself, I'm on a beach doing some calculus problems. Because of course, those two things often go together. So how do you know when you can do it? And the answer is you look for 2 things. So you look at your bounds. Notice that the bounds are all numbers. If you ever have it so that the bound is like the inside is a function of theta to another function of theta. When you have that, you can't separate them. The other thing you need is to say, I can write the function as something which only depends on theta, which in our case is 1, times something which only depends on r, which is the minus root 3r squared. So when you have those 2 things, the bounds are all constants, and you can pull the function apart as a product of 2 functions, then you can separate. But again, that's not a requirement. All right. So those were the 2 problems I pointed out, but I know that there were other questions. So here we go. Here's some other questions. So one of them, were about line integrals. And there's 2 types of line integrals, so we should talk about both. So you have your non-conservative, and then you have your conservative. And I probably did not give myself enough space for both, but that's okay. I will go through and do the best I can. Now, what is a non-conservative? Essentially, it's something where we can't use the fundamental theorem of calculus in a cool way. And that is that we have to just sort of just say I got to do the integral. I don't really have a choice. So how can you identify things which are going to be not conservative on an exam? If you have simple functions, and you have a very simple parameterization. If you see that, odds are pretty good it's not going to be conservative. Because if things are simple, the reason it's simple is because you have to give you something you can actually work with. So when you see things like, e to the x cubed with an arctangent, okay, that's not simple. If you see x squared, that's simple. So when I'm talking about some very, very straightforward functions. And so when you have that setting, and that's what you look for, you say, all right, what is this? Well, again, these integrals have several forms. There's the integral, sometimes we write it as m dx plus n dy. And I really like this, and I'll come back and explain why I like to write it in this way. Sometimes you'll see it as the integral of f dot dr. And sometimes you'll see this as the integral of f dot t ds. And these are all definite integrals. There's no indefinite integrals in multivariable calculus. Everything's definite. So these integrals all represent the same thing. They're just expressions of the different forms of the integrals. I've written the 2-dimensional version. There's a 3-dimensional version as well. Now, what do you do? What do these represent? Oftentimes, where you'll see this is you can interpret this as being a work. So, whoops, you didn't see what I wrote. I wrote the word work. So if you see a problem that has a work involved, then that means you're doing some integral here. It could be conservative or it could be not conservative. It just depends on the problem. So just check the problem and take a look. Now, how do you do these integrals? Well, let's try to make something up. So since we're doing not conservative first, remember, simple functions, simple parameterizations. So we could have a function, so for example, maybe f, I don't know, x plus y and x squared. Okay, something easy. And what is c? Well, c, again, it's a simple curve, so we have to parameterize the x and the y. Okay, let's do it as minus t squared and t cubed. And where t is between -1 and +1. So whenever you have a curve, you have to have a couple pieces. What's the parameterization, and where does time run from? So if this is the problem we're asked to do this line integral, and we say, oh, okay. Now, one of the things is you should check to see if it's conservative. Now, there's a couple of tests. One is you can say, okay, let me try to build the potential function, which is if you take the antiderivatives. So here, if you take the antiderivative with respect to x, you'd get a half x squared plus xy. Here, if you take the antiderivative with respect to y, you get x squared y. Those aren't compatible in the sense that when you look at the parts that involve both x and y, the two slots don't match up. There's another way to test if something's conservative, which is you come to your first entry and you say, what's the derivative of this with respect to y? What is the derivative of x plus y with respect to y? It's 1. Go to your second entry. What's the derivative of x squared with respect to x? 2x. If those don't match, not conservative, don't try anything that's a conservative technique. Okay, so we're doing not conservative techniques. So that says that this integral here is the integral along the curve of, so m is the first slot, x plus y dx, and it's your second slot, x squared dy. And the way you do this is you always put everything in terms of t. So your curve, put in your bounds. -1, +1. Everything that's an x gets replaced by what x is. So minus t squared. Then everything that's a y becomes what the y is. So that's t cubed. The dx, that's x prime. So you say, okay, what's the derivative of minus t squared? Minus 2t. All right, now you go to the next term, x squared. So that's minus t squared squared times dy. That's y prime, 3t squared. And then at the very end, you put a dt. So if you have a non-conservative function, you just literally take every piece and say, okay, let's put everything in terms of t. Your bounds in terms of t, x in terms of t, y in terms of t, dx in terms of t, dy in terms of t, so forth and so on. Same idea if it's a three-dimensional thing. And now what you have is you look at this and say, oh, this is not a bad integral. I mean, it's not an exciting integral. We'd have -1 to 1 of 2t cubed minus 2t to the 4th. Then here you'd get plus 3t to the 6th. And you evaluate that, and you get an answer. And after this step, there's nothing really exciting that happens. If it asks you to simplify your answers, simplify them. If it doesn't ask you to simplify, dealer's choice. If you want to simplify because it's like, hey, I love simplifying, woohoo, then go ahead. And if you don't, just like, yeah, I think I'll leave it as it is for now. Okay, so that's the non-conservative types of line integrals. So that leaves us with a different type, which is the conservative type. Okay, so how do you recognize conservative type? Well, one thing is you should look for crazy curves. In other words, like a parameterization, if you see a parameterization like, holy cow, that is just such a weird parameterization, we are trying to send a signal to you. We are just sort of thinking, please see that this is a crazy curve. Do not try to integrate this the way that you would for a non-conservative. It would work. It would absolutely work. But it would be very, very long. It would take up a page and then a page of scratch paper, maybe a couple pages of scratch paper. The other thing is that you have usually non-trivial functions. So functions which are more complicated to work with. So when you see a complicated curve, a non-trivial function, you should start thinking, all right, that sounds like something where I want to use conservative. Okay, so how do we do that? Well, let's try to plot an example. Let's suppose our curve, maybe they'll say the curve starts at the origin and ends up here at 0, 1, and they don't, give us the full parameterization, but they say, here's the picture for what that curve does. And then you say, all right, you want to do an integral along that curve. That should make you suspicious. So if you look, for example, I think there was an exam problem from a year ago, from last fall, where it was, here's a sawtooth curve. It went up and down 19 times. That's a curve that you're like, I don't want to deal with that curve. Because if I did that as an actual integral, I'd have to parameterize each one of those segments. I'd have to do 19 individual integrals. That takes a lot of time. There's only a little bit of time in the test. And we know that there's only a little bit of time. Okay, so crazy curves, that's a signal. Non-trivial functions, that's a signal. So let's write this down. So this is the dangerous part. We're trying to come up with a non-trivial function on the fly that actually works. So now it's not so bad to come up with these things. You just have to sort of go in there with the mindset of what's happening here. Okay, so here we go. Here's a function. You'll see this 1 over 1 plus y squared, that's non-trivial. But I can go even crazier. So how do you do these integrals? So there's generally two approaches to take. And we've done both in the past. So I want you to know that there are two approaches to take, should you encounter one. So approach number one says, find the potential. Okay, so what does that mean? Well, we're trying to find something where capital F is equal to the gradient of F. So I'm looking for that little function F. Essentially, you can almost think of it as what we're trying to do is like, what's the antiderivative here? Okay, so we say, all right, what should be true is that this should be the derivative with respect to x. Okay, that's x cubed plus x squared y. And this should be the derivative with respect to y. So what I'm doing is I'm integrating here with respect to x. I integrate here with respect to y. X squared y plus arctangent y. And now we check, are they matching up? Which is to say, do the pieces which have more than one variable involved, are they consistent in the two entries, or if there are three entries? In this case, they are. So I say, okay, what I need is I need an x cubed. I need an x squared y, just one of them, because it's going to work for both slots, and an arctangent y. So our little f is x cubed plus x squared y plus arctangent y. Now, I now can see I omitted one thing about my curve. Do you see what I forgot to say about the curve? Well, what I forgot to do was orient it. Because if you just saw this on a piece of paper, you say, well, which way did you go? Did you go from 0, 0 to 0, 1 or 0, 1 to 0, 0? Now, I was drawing it, so I was trying to imply an orientation. Here we go. There's our, I'll put a little arrow. Now it's oriented. So keep in mind, orientation becomes important when you do a lot of these problems. So that means we start at 0, 0. We end at 0. That's supposed to be a 0, 1. It looks like a 0, comma nothing. All right, 0, 1. So this integral along the curve of f dot dr becomes x cubed plus x squared y plus arctangent of y, evaluated from 0, 0 up to 0, 1. Well, when you plug in 0, the nice thing is when x is 0, these two terms are gone. So x is 0 in both of the slots, so these two terms are going to go away. You'll have arctangent of 1, and then you subtract arctangent of 0, and arctangent of 1 is pi over 4. So this is arctangent of 1. Now, in case you're wondering, how do I know arctangent of 1 equals pi over 4? Well, I've been taking calculus now for a couple semesters, and I keep seeing that somebody really loves arctangent, so I decided to memorize it. But the other way to do it is just to remember, okay, if I'm looking for arctangent of 1, that's the same thing as saying tangent of something equals 1. What's the something? And then the answer is 45 degrees, and then we turn into our calculus, and then we say pi fourths. Now, I said that was one way to do it. So option number 2, sometimes you can't find a potential. And you're probably thinking, come on, I'm pretty sure I can find it. No, we're pretty good at coming up with stuff you can't do. So you can show something's conservative without finding the potential. So this is not a case of that. And I'm not going to try to come up with one on the fly. They're a little bit tricky. So the other thing you can do is you can change C. So if you can't find the potential, you can just change your curve. So that's the second option. Now, you might say, if I can't find the potential, how do I know if it's conservative? Well, this process was finding the potential. There's a process to test if it's conservative, which is you come here and you look at m sub y and you look at n sub x and you compare. When you take the derivative of the first term with respect to y, what do you get? 2x. When you take the derivative of the second term with respect to x, what do you get? 2x. If they match, it's conservative. So you can show something is conservative even if you can't find the potential. So in our case, how do we change C? The answer is make C the nicest curve you possibly can. What's the nicest curve that goes from 0, 0 up to 0, 1? Just the straight line segment up. There's our new curve. So we can change our curve. Now, we can only do that when we're conservative. If you're not conservative, don't do it, because it's not true. So in particular, we have that this is the curve 0, comma t, where 0 less than or equal to t less than or equal to 1. So we changed our curve. We now have a very easy curve. We can parameterize it very simply. And if we do go ahead now and put in integral from 0 to 1, well, we just integrate. We have this term times our dx. But notice everything in here is 0. So it's going to be 0. And then this term will be what? Well, it'll be 0 plus 1 over 1 plus t squared. So that is what's going to happen when you now do the m dx plus n dy, put everything in terms of t. And you say, oh, that now is a really easy integral. The hard stuff disappeared. And so it's arctangent of t from 0 to 1, which again is pi over 4. So those are your two options. So this is what you should do should you encounter a line integral. Something up here will help you get through it. All right. Let's see. I'm trying to make sure I hit everything. So let's talk for a second. There's two more topics that I recall that people wanted to just go over. One of them was center of mass, and the other one was spherical / cylindrical. And we can put these together, because they oftentimes go together. So when we're talking about center of mass, it's like we're trying to find that nice balance point where everything works out very nicely. So that would be, for example, our x bar, y bar, z bar, say we were in 3 dimensions. And how do we find it? The way I like to think about center of mass is like I'm doing a weighted average. So I'm taking my shape. It might be 2-dimensional, it might be 3-dimensional. I break it into little pieces. I'm going to say I'm going to weight the average of the location based on the size of my little piece. So the way you find this, let's just suppose we pick on z bar. It often gets picked on, that poor z bar. Let's do the triple integral over a solid of your z times your density times your dv. Now that's just, we call this in physics, I like to say that we call it in physics like I'm a physicist. I haven't had physics like in 25 years, so I hope things still fall down. All right, so that's called the moment with respect to the xy plane. And then we divide it by our delta dv, which is our mass. So this is why we call it an average, because we're weighting things, but then we divide out by the total that there is. So it's a moment divided by mass. Now, a couple things to look for is if you do see a center of mass problem, almost always there's a little bit of symmetry built in. Now, I'm not going to say every time. We have had examples. When there's not symmetry built in, it's because that the shape itself is so easy to work with, and the density involved is so simple that we don't mind you doing a lot of integrals. We are aware that you have problems on this, multiple problems, so we try to keep our integrals very simple and try to keep it down. So when we're looking for symmetry, or what's the type of symmetry we look for? In 3 dimensions, a lot of things you look for are rotational symmetry. So what's the symmetry, say, with respect to the z-axis? And this is by far the most common. So if you say, oh, look, I can take my shape and I can spin it around the z-axis, that means it's symmetrical with respect to the z-axis. Your center of mass has to be there. So keep an eye out for that. But once you understand how to set the integrals up, then there's really nothing to do with the center of mass. You just do the integrals and you're patient. Make sure your answer is somewhat realistic. If you are doing a center of mass problem, and I keep saying this, and I hope you should pause at the end of a problem. If you do a center of mass problem and you find out that your center of mass is up there, that's a problem. Because your center of mass can't have everything be on one side of it. It somehow has to be balanced out. So that roughly, I don't want to say half is on one side, half is on the other, because that's not what the center of mass does. But you should have stuff on both sides. So make sure your answer is somewhat realistic. As far as spherical and cylindrical coordinates go, the nice thing about cylindrical is it's a polar coordinates plus z. So if you remember how polar works, and we've had a little bit of practice because we did this in Calc 2 as well as in Calc 3. So if you remember how polar works, you've got your r and your theta. So x equals r cosine theta, y equals r sine of theta. So that's polar. And then you just remember that z equals z. Now, when do you switch to polar? When do you switch to cylindrical? So the clues that you switch to cylindrical are you look for things like cylinders. But really, in general, what you look for is if you see lots of things written down with x squared plus y squared. Because x squared plus y squared is like geared to work in polar. Because what's the reason that we love x squared plus y squared in polar? The reason we love it is because addition is hard for us to get around. But when you have x squared plus y squared, we compress it down to a single thing called r squared. We've removed a plus sign. Life gets better. So now we're down to r squared. Okay. So if you see things like this, in particular, you see cones or you see bowls. Now, cones also show up in spherical, but I will say if you see cones are fairly reliable, but if you see a cone like this, like an upside down cone, then you got to go to cylindrical. Upside down cones work terrible in spherical. If you see any shape, any kind of bowl, so when I talk about bowl, things like z equals 2 minus x squared plus y squared. I don't know why I like upside down bowls, but all right. So that's more roundy at the top. So that's a signal to switch. Oh, sorry, I'm a little bit off to the side. So what about spherical? Now spherical gets more interesting. In spherical, what do we have? Well, you really have 2 angles plus the distance. And the distance we call rho. And so what I like to remember is 3 things. Z equals rho cosine phi, r equals rho sine phi, and x squared plus y squared plus z squared equals r squared. Sorry, rho squared. And once I see that, then that's enough for me to get me through all the shapes that I'll encounter. So what can you encounter in spherical? Certainly things that you look for spheres. And in particular, there's 2 types of spheres that are pretty good, namely spheres centered at the origin, Or there's a type of sphere where you, for example, have the bottom of the sphere sitting on the axis, sitting on the xy plane. So a shifted sphere up in the z direction. Cones also work really well. And yeah, that's about it. It's spheres and cones. So when you see that, that's probably an idea that you're working with spherical. Now, by the way, cones can include things like the xy plane. So a couple of things to keep in mind. If you do need to integrate in the coordinate systems, make sure you remember your various pieces. dv is r, dz, dr, d theta. This is the same r that shows up in polar. In spherical, what do you have? Well, do you remember? Rho, sine of phi. Good. Rho, d phi, d theta. Yeah, you got it. Good. Anybody go home and like, hey family, let's sing together. This is helping me study for my calc exams. You know, it's important. Yeah, no, I'm not recording to make fun of you. This is helping me. All right. So anyways, so one of the things to recognize, I said if you see a lot of things involving x squared plus y squared, that is both in terms of what describes your region and also in terms of your function. That's a good sign for polar. The similar process is showing up when you see x squared plus y squared plus z squared. So if your function involves like x squared plus y squared plus z squared, that's a good sign that you should be working in polar coordinates. All right, so so we should work on switching. The problem with switching is it gets tricky. Okay, all right, we'll do this. So suppose you have the integral from -1 to +1, integral square root of 1 minus x squared to square root of 1 minus x squared. There's a negative downstairs. Hard to see. There's a negative. And we had the integral from 0 up to the square root of 4 minus x squared minus y squared. And we wanted to integrate, 1 over the square root of x squared plus y squared plus 1 dz, dy, dx. Okay, so suppose we wanted to do this. Now, why might we want to do this? Well, this, for example, this could be a mass. So I have a density. Here's my density function. I'm looking for a mass. So how do you switch? Well, if you're going to switch, the key idea is to figure out what's your shape. So you think about what your pieces are. So here, I can look at these two pieces, and hopefully you started to recognize these things. What do those look like in the xy plane? It's a circle. So I'm going from -1 to +1, square root of 1 minus x squared, minus square root of 1 minus x squared. So that's my shape. So now I'm here, which says that my region I'm integrating over in the xy plane is a circle. So this is my circle here in the xy plane. And now I'm going from 0 up to, what's this? So it's z equals something. What does it correspond to? It's a sphere. It's a sphere. See, if you square both sides, you get 4 minus x squared minus y squared equals z squared. You move the x squared minus y squared across. X squared plus y squared plus z squared equals 4. Which says it's a sphere, but it's not going straight down. It actually goes further. Okay, so we're going up to that sphere. So this is a cylinder with a sphere attached. Now, the question becomes, what coordinate system do we want? So to help me when I'm thinking about spherical and cylindrical, what I like to do is I like to imagine slicing. And I call this the RZ plane. And in other words, I'm just sort of saying, what do I look like if I just take a slice and I'm coming off of the z-axis in some direction? So when I do that, I have the z-axis, and r is just how far off the z-axis I am. And what we'll see is we'll see a circle on the top, to a certain point, and then we'll go to 1. So that's our region. And then we spin around. So the question becomes, what coordinate system makes sense? Well, we didn't talk about everything about spherical that we should have. The other thing we should have talked about is phi. Now, phi says, how do you relate to the positive z-axis? Phi equals 0 is straight up, and then you come down. And whenever you're trying to set phi, this picture helps tremendously. Look at that slice. That will help you figure out what phi should be. When you get to pi halves, that's here. Now, the problem in spherical, yes, we have a sphere, but notice we change that surface of what we'd hit if we came straight out from the center. Because in spherical, everything comes out from the center. Which says, if we were to do this in spherical, how many integrals do you have to have?
2.
You'd have to have 2, because you'd have to split it up based upon what you hit when you come out from the center. That sounds like twice as much work as I want. But when we do it in cylindrical, we're okay, because what's going to happen is we're going to go straight up and down. We're not going to have to split it into 2 integrals. There's something else that says you should switch this to cylindrical. What is that? That's the x squared plus y squared there. Again, x squared plus y squared, think cylindrical. So this becomes, well, in the interest of time, integral, 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 1 over r plus 1. This dz dy dx is our dv. So that's r dz dr d theta. And then our bounds are theta is 0 to 2 pi. That just says you go all the way around. R goes from 0 to 1. And then z goes from 0 up to the square root of 4 minus r squared. Now, maybe we can't finish this one, but sometimes you don't have to. Sometimes we're just happy to say, set it up. So be ready. Your problem just might be set it up. Might just be change the order of integration, and so forth and so on. I guess I'm over time. Thank you. Good luck.